Hello, and welcome back to section 16. In this video, we'll be going over example 3. Example 3 asks us to solve a circuit diagram for v of t for t greater than 0. So we're going to have our first circuit where we have a forcing function, and we have to actually find the differential equation ourselves, find the particular response, and find the natural response. Additionally, we're also going to have to find the initial condition. If you remember back in section 14, you were given the initial condition. You were told that the initial voltage or the initial current was a certain number. But now we're going to have to find it on our own. So let's jump into that. So I've redrawn the circuit here. So take note that the picture has 250 millifarads, which that's the same as a quarter of a farad. So I wrote it as a quarter of a farad for convenience. So the first thing you want to do when you're solving one of these circuits is you generally want to get the differential equation. And that means we're going to want to get the derivative form of our energy storage element. So if it's a capacitor, it is I equals C dV dt. If it's an inductor, we're going to use V equals L di dt. And then write your capacitors in the same form. So I equals V over R. So this means we're going to be doing Kirchhoff's current law, because we want to get all of our I's together so we can use a common voltage, which is convenient because we're trying to find voltage. So this voltage is described across this capacitor. Normally they're going to be across your energy storage elements, but they don't have to be. Because everything in this is in parallel, it's actually the same voltage across everything, so it doesn't actually matter in this case. So to get our differential equation, we're going to use a KCL equation. And I'm going to set this up such that we have our voltage V at the top here, and we have a ground down here at the bottom. So we're going to do a KCL at V to get started. And that is current in equal to current out. Our current in is IS. So IS was given to us, I'll write that over here real quick. It is 10e to the negative 2, 10e raised to the negative 2t, u of t. So that u of t, if you remember from section 15, means that this will not be turning on until we get to time equals 0, or just after time equals 0 technically. But for right now, we're just going to use the generic I of s coming in, and then I'm going to assume these two go to 0, so we'll assume they go out. So in that case, we're going to have V over 1 ohm, and then the current through our capacitor will be this equation over here, C times dV dt. So our C is a quarter, and then dV dt, so we're going to just use the V here, so it'll just be dV over dt. But if this was Vx, we would say dVx dt. So we would use the appropriate voltage. It's not always just V. Okay, and then we want this in standard form, which means we want to get a coefficient of 1 in front of our highest order derivative. So that's this one. So we want to get rid of that quarter. So we want to multiply by 4. And I'm going to do a rearranging while I do this as well. So we're going to get dV dt plus 4v equal to is. So this is our standard form. I left the is on the right side because it is not a function of v. It is just going to be our forcing function. So this is our right-hand side for right now. Oops, made a mistake. That needs to be a 4 over there. That 4 has to distribute everywhere. So it's 4is. So don't make that mistake. Okay. So now we have a derivative, and you could plug in is, but I'm not going to, and I'll tell you, and I'll explain why in a second. So the next thing we're going to do is we're going to start trying to find v of t for t greater than 0. So we're going to assume that t is greater than 0. And that means that our function is going to look like v of t is equal to v particular plus v natural. So we know that, we talked about this back in section 14, that these first order linear differential equations will take this form. We know that v natural will have the form a e to the s1t. So our goal is to find v particular a and S1. So we're always going to find the constant of integration a last. So we're going to find S1 and v particular. So generally I will start with finding, well, S1 is pretty easy, so we'll start with S1. So if you followed along in example 2, you'll note that if we look at this term here, that is our S1. So it is, again, we can write this over here as generically dx dt minus S1 times x equal to our right-hand side. So S1 is right here. So this is a minus 4. So because it's going to be minus 4 to get us to a negative S1. So we know that S1 is equal to negative 4. So we don't have to do much math there. We just looked at our differential equation. So we can rewrite what we have so far. V of t equals v particular plus a e to the negative 4t. So we always want to find a last, which means the next thing to find would be v particular. So v particular can be found using the techniques that we used previously. So now we need to know what our right-hand side looks like. So g of t will look like 4is, and when t is greater than 0, so that's going to be 4 times 10 e to the negative 2t. Because when we are at time greater than 0, this is on. So this is 40 e to the negative 2t. So we check real quick. Negative 4, s particular, is negative 2. They do not match, which means we can use substitution. So we'll just use substitution to find this. So differential equation is right here. So we're going to say that negative 2 v particular plus 4 v particular is equal to this right-hand side, this 40e to negative 2t. So, oops, sorry, I looked away from the screen there for a second. All right, so let's talk about, sorry the screen's freezing on you there. There you go. Let's talk about, so again, this is just dv dt, but we replace d dt, so this is equal to d dt. And so we take this equation and we sub this out. We replace v with v particular, because that's what we're trying to find. There's our 4, and then we have 4is. At t greater than 0, this is what 4is is equal to. Let me get my mouse out of the way there. There you go. So now we solve for v particular. So we're going to get v particular is equal to, so this becomes a 2. So we get a 40 divided by 2 e to the negative 2t, which is just 20 e to the negative 2t. So that is v particular. So we bring down our function again, and we rewrite it. V of t is equal to 20 e to the negative 2t plus a e to the negative 4t. And this is for t greater than 0. No, you can't see that, sorry. There you go. So the only thing we have left to do now is find a. But when we go find a, we need to know, generally what we want to know is what is v at 0 plus. So that's what we want to know. Because once we know what v at 0 plus is, we can plug in a bunch of zeros and we'll be in good shape. So v of 0 plus through a capacitor is equal to v of 0 minus. Why is that? So if I have some voltage, say it's at 10 volts right before we switch, if it changes instantaneously without much time expiring, we get basically infinite voltage. So you cannot have a voltage change without time changing. So therefore, through a capacitor, the voltage before and after a switch must match up. Otherwise, you have infinite current, because you'll get a change over 0. Or however you want to interpret that. Basically, you'll get a number over 0. So v of 0 plus is equal to v of 0 minus through an through a capacitor, not an inductor. So we are working through a capacitor. Okay. So V of 0 minus, if I can find that, then I know V of 0 plus. V of 0 minus, we can do that. I'll do that over here on the right, just kind of off to the side. So this would be for t less than 0. So when t is less than 0, we're also going to get a similar function. We're going to get V of t equals V particular plus. So I'll write that real quick. We're not going to solve this full thing. We're going to assume steady state. What that means is that the natural response has gone away. Basically, we assume that it has been turned off or turned on for a very long time. And because of that, V natural has decayed to 0. So then V of t is just V particular, and we know how to find V particular. So V particular when time is less than 0. Again, we're going to go get our differential equation, dV dt. But this time, what is G of t? G of t is no longer, so it's still 4is, but is for t less than 0 is 0. Because is goes to 0. Hasn't turned on yet. So therefore SP is also equal to 0. So if I go through the long form here, and this is also equal to d dt, then I will get that 0 V particular plus 4 V particular is equal to 0 on the right hand side. You do some math, you find out that V particular is 0, which means that V of t is 0. So for all time t, including V of 0 minus, is equal to 0. And because it's through a capacitor, that means that it's also V of 0 plus. So I'm going to stepping through. This is the form for our differential equation. We have a differential equation. This form will be on for before and after the switch. I assume that we have been, in this case, off for a very long time. So steady state. Our natural response therefore drops out to 0, and we are left with V particular equals, the function here, Vt equals V particular. We are looking for V of 0 minus, so I need a function of t here. I know how to find V particular. It's the same stuff that you've been doing. So I find my S particular, but because my force function is a 0, then it goes to 0. And then we eventually end up with just V of t is 0 for all time before the switch. So therefore V of 0 minus is 0. Because it goes through a capacitor, V of 0 plus is also 0. Because V of 0 plus has to match V of 0 minus. Alright, so back over here to our left-hand side. So therefore I know that V of 0 plus is equal to 0, which is equal to 20e to the 0. So when I put in a 0 here, this is going to go to 0. So it's going to be basically just 20 plus a e to the 0. And when I do this math, I'm going to get 0 equals 20 plus a, or a is equal to negative 20. And then I write my function one last time. V of t is equal to 20 e to the negative 2t minus 20 e to the negative 4t. 4t greater than 0. And that is our answer. Alright, if you have any questions, feel free to contact me.